going to have what we call, today we are talking about what's this thing called the Kubernetes. We're talking about one of the most industry that is booming and it's called DevOps. And you probably could have heard about containers, Dockers, Kubernetes. And it's one thing that is now taking place in the world, because those days we used to have like system administrators. You used to have people who control how code is deployed. But now we have something called containers. We have virtual machines, but we have several operating systems, and now we have containers. Like a container may have as many virtual machines as possible. Dockers and then Kubernetes. These are one of the things that in the DevOps field you will meet them. So what is a container and why do we need to use containers? How Docker helps using containers and Docker commands, orchestration, swarms, and Kubernetes, because Kubernetes is a software orchestration platform. And then we have Docker networking and security. We want us to admit these things that are currently making sense to the world. Now, all those things involve using virtualization, because we are doing virtual reality. We are deploying things on virtual things. We are deploying our devices on virtual devices, virtual platforms. So, what are the advantages of virtualization? One, we have minimizing hardware costs. Virtualization minimizes hardware costs. Like an example, I have very many virtual machines on my computer, and you find one virtual machine of 20 GB. I'm running Windows Server 2016, Linux Server, Ubuntu Server. I'm running very many operating systems, but on 20 GB, and I'm virtualizing them. If in real terms, I would have had several computers running those OSs. So multiple servers on one physical hardware. They easily move virtual machines to other data centers. It is very easy to move the virtual machines to other data centers compared to moving a very full computer, a full server computer. But you have your server, your virtual machine. You can easily write a command or a script that moves it from San Francisco to Dublin in Ireland, to Budapest, or to Norway, or to China, Shanghai, but with just a simple command, and you reach there and find your computer is there, because you use the virtual machine. You can access your virtual machine when it is far away from you. So consolidate idle workloads. Usage is burst and asynchronous. Increase device utilization. So this virtualization makes sure that the usage is device utilization. Yeah. And virtual machines conserve power. Yeah, because we actually I'm actually using one computer to run several operating systems at the same time. Yeah, and we are just using one power, only one, and running like 7 computers at the same time, 7 servers. Another one, we have free up unused physical resources, easier automation, lower operation expenses. Yeah, because I'm telling you that simplified provisioning, we have administration of hardware and software. We are just using one. Like here, the demonstration I'm showing is that this is USA and America, this is Europe and Asia. You can easily move your virtual machine here, jump to the US, jump to Europe, and jump to Asia, and then jump back. That's the good thing with virtual machines. And so we have scalability and flexibility. I told you about that. I have a virtual machine. I run Ubuntu Linux for my robot operating system. And I also do some, on that same virtual machine, I run Kali Linux for for ethical hacking. Then I run Windows Server for my practice and likes and stuff. And when I get a new operating system and I want to test it out, I just use the virtual machine, I install it and then see how it works, and I'm good to go. Yeah. Oh, we got to problems of virtualization. Virtualization also has a problem. It is good, but it has a problem. Now we're going to see something. We have a virtual machine. We have an app. We have OS. Then VM app. We have several virtual machines running on the same physical hardware. And one thing that is called a hypervisor. I remember back in 2013 when Microsoft had launched Windows Phone, and they chose me to be one of the Microsoft student partners of my institution, and it was a very growing task for me to handle. And the computer I had didn't have hypervisor enabled, so I had to first go into the BIOS and enable the hypervisor for it to be able to run the virtual machine of the Windows Phone. And so that is so. We say that each virtual machine requires an operating system. Each OS requires a license. Exactly. Apart from Linux, because Windows requires a license. Each OS has its own computer and storage overload. Needs maintenance, updates, yeah. So VM tax equals the added cap expenses plus operation expenses. So we see the license plus the operation expenses needs maintenance because the computer is doing a lot of work. The solution: containers. Run many apps in the same virtual machine. That's because you having very many virtual machines is not good. So you have to make sure you run many apps in the same virtual machine. These apps share the OS. It's overhead, but these apps can't interfere with each other. They can't access each other's resources without explicit permission, like apartments in a complex. Yeah, you can see an example here. So this is an example of how how the virtual machine has very many applications running. Okay. Containers. So we have the virtual machine. We have the container. Now we bring in the element of having containers. We have the container, and each app is running in a container. And then we have the shim and then the operating system. Now see, we're changing something from here. See here we're having OS, various OSs, and then various applications running in the virtual machine. Now we come to this issue of having something like we have one OS, we have the hypervisor, then we have the OS, then we have the shim, and then we're having several applications running in the containers. Like here, like you have an app like Facebook, like WhatsApp, like Netflix, like Tinder. So, and they are all running in the virtual machine. That's how now they are being hosted online, because we have, or like a company that has very many apps running, like Google. You find they have one operating system and they have several applications, they have several containers, and they are all in one virtual machine. So multiple containers run on one operating system on a virtual stock physical machine. All containers share the operating system. That means we have shared resources, and the license is one and the operating frequencies is one. Containers are isolated. They cannot interfere with each other. They own file system, stock data, own networking, they are portable. We continue. Containers have all the good properties of virtual machines. They come complete with all files and data that you need to run. Multiple copies can be run on the same machine, all different machines. This is why we need containers, because I started showing you the virtual machines until now, when I brought you that you can have one virtual machine And then you have several containers. So we have the same image, multiple copies can be run on the same machine or different machine. Same image can run on a personal machine in a data center or in the cloud. The operating system resources can be restricted or unrestricted as designed at container build time. Isolation, for example, show process. Command in a container will show only the processes in the container. It can be stopped, saved and moved to another machine or for later run. Virtual machine against containers. Criteria. Virtual machine, we have containers. Images, size. The virtual machine is 3 times the container. Is just virtual machine is 3 times the container. And now the virtual machine take greater than 10 seconds to boot. Container takes 1 second only. Computer overload. Virtual machine greater than 10% of the computers, but the container takes only 5%. Disk I/O overload less than 50%, greater than 50%, by the containers negligible. Isolation good for the containers is fair. Security low media. Containers very highly secure. OS flexibility is excellent. For the containers is poor. That's why the virtual machines have the OS and they run very many containers. Management excellent, it is evolving there. So that's where we have Docker. Docker. It provides isolation among the containers. Now we have very many containers running on the virtual machine. And what helps those containers to run isolated? That is Docker. The Docker helps them share the OS. Docker has a Docker worker, and the Docker worker manages the containers. It was developed initially by docker.com and is downloadable for Linux, Windows, and Mac from docker.com. So you can download it, Dockers, and you begin using it. We remember like a ship, a place where ships land, and that's called a docker, a dock. So these guys also had to say, okay, we have very many applications. Those apps are like ships, and we want them to dock on the shore. And that's why they came up with the Docker. So we see this one, app 1, app 2, app 3. And these are containers. So these containers are managed by the Docker, and it helps them to interface with the OS. So the Docker engine runtime, 2 editions. We have the community edition, free for experimentation, and the enterprise for deployment with paid support, written in Go programming language from Google. What? Now, when Google brought the Go language, I was in my 3rd year, 2014. And I didn't know what Go language could do, because we had an event and these guys were teaching us about how to use the Go language. And none of us saw something that this was something actually that was going to take over, that was coming to take over. And those who learned Go language are fun now, because Dockers are created from this. I'm taking some chocolate. Yeah, you can join me. Docker Docker engine components. We have the daemon. What a daemon is? A daemon is a process that, the same way like we have the demons in the physical reality, in the spiritual reality, so is this daemon. The daemon cannot be killed, and it will keep running in the background. So that's why the computer scientists had to coin this what called daemon. Sometimes I would be saying this demon because I use mostly Gradle, and I always meet this word Gradle daemon, and I always call it the Gradle demon. Container execution logic. So we are looking at the various parts of the Dockers. And then we have the rank, lightweight runtime command and interface. Then we have the shim. It is a rank exists after creating the container. The shim keeps the container running. Keep standard in, standard output open. People have never done C++, don't know what these things mean. std in, std out. C and C++ access these libraries directly. When you're programming in Java, C#, these things are already implemented for you, so you don't have to import these things. So we have the Docker client. Oh. What is going down? Okay. So we have the Docker client. Then we have the daemon. Then we have the Docker engine to receive the instructions, give them to the daemon. There is container, gives image to rank. Then we have the shim, multiple shims, multiple ranks, enables daemonless containers. And then we have the containers, daemonless containers. Then we got image registries. The containers are built from images and can be saved as images. Images are stored in registries, local registry on the same host, the Docker Hub registry, globally shared, and the private registries on docker.com. When a component not found in the local registry is downloaded from specified location. If the Docker registry images vetted by Docker. Now somebody may think the images are like the PNG, the JPG, the what? No, images are in .iso file format. Those are the images we are talking about. Each image has several tags, version 2, latest. Each image is identified by its 256-bit hash. So we have to talk about the layers. Each image has many layers. And the image is built layer by layer. Nara can go through face. Okay, Kali, we continue. We have each image has many layers, and each image is built layer by layer. For example, Ubuntu is installed, and Passion Package is installed. You get several layers. Then a security patch, the person is installed, and the layers can be shared among the containers, many containers. You get it? We see the Ubuntu, the Python, then the patch, layer 1, layer 2, layer 3. Building container images. How do you do that? Create a Docker file and describe the application, its dependencies, and how to run it. Then from Alpine, start with Alpine Linux. Who wrote this container? Maintainer equals dash dennis.moz@gmail.com. Use the apk package to install Node.js npm apk add update node.js. Copy the app file from the build context, set working directory, install application dependencies, expose 8080, open TCP port 8080, entry point node, then the app. Run npm install, copy source, run apk add, then from Alpine, that is the layer 1, layer 2, layer 3, layer 4. Yeah. Then we go to several Docker commands. We have Docker run, it runs the specified image. Docker container run. And we have Docker container LS and more like a Linux command. This is the running containers. Docker container exec run a new process inside the container. Docker container stop a container. Docker container start a stopped container. Docker container rm, more like a Linux command, delete a container. Docker container inspect. The inspect shows information about the container. Now go to Open Container Initiative. This is a company called CoreOS. Define alternative image format and container runtime APIs. Iterate the formation of OCI, Angular 20%, govern container standards. And everyone, including Docker, is now moving to Open Container Initiative. Open Container Initiative. Then we have a swarm. You know, among the most swaggerific people are the computer scientists. All the terms they use are related to the real world. Now, you would mind how would somebody say that I have containers? Now, the containers that we use, because I have various containers. I have cups, I have plates, I have buckets, and as in the future, we're going from chassis buckets, and then you wonder, computer scientists are one of the most humorous people. If you get one as your husband, you have the best person you can get. was a friend. Very humorous people. Now, orchestrating thousands of containers, that's called a swarm. It's like a bees. So a swarm is a group of nodes collaborating over a frame or a network. There are two modes for Docker hosts. Have a single engine mode. Then we have a swarm mode. A swarm, a service may run on a swarm, and each swarm has few managers and dispatch tasks to the workers. The managers are also workers because they execute tasks. We're going to see how it looks like. Now here, we have a single Docker. That's how they made it like a ship. Single engine mode. Then we have a swarm. We have very many swarm nodes, various containers. And swarms, the manager selects a leader who really keeps track of the swarm. They assign tasks, reassign failed workers tasks, and other managers just monitor passively and re-elect the leader if the leader fails. Services can be scaled up or down as needed. Several Docker commands. So you can't imagine that computer scientists create these things called Dockers, and these Dockers they assign them responsibilities of the swarm manager as workers, and then they have other swarm managers with tasks to monitor the failed swarms, the failed workers. What? So, Docker service, several Docker commands. We have Docker service that manages services. Docker swarm, we manage the swarms. Docker node, manage nodes. And then we have the Docker swarm commands. Docker swarm init, you are initializing a Docker swarm joint token. Docker swarm node LS, you are listing all the nodes. Docker swarm, Docker service create, you are creating a service. Docker service LS, you are listing the service is running that have been created. Docker service PS, Docker service inspect, Docker service scale, and update. Remove, you are removing it or deleting a service. Now, Docker override networking. We're going to move to the next thing. We're now moving to Kubernetes. Kubernetes is mainly an open source orchestration alternative, and you can see it was also released by Google. Original source released by Google. The Cloud Native Computing Foundation project in Linux Foundation. Almost everything is running on Linux. And if you have to use Kubernetes and Docker, you will have to write commands in Linux terminal. So there is no way you will hide from Linux if you want to go deep in computer science. Okay, so Kubernetes, but as I talk of now, we shall meet again, talk about Kubernetes.